Hi. I've been working quite a lot on the VESC stuff recently, and the reason I haven't published or pushed any changes to this repository is mainly that I've been adding a lot of new features and broke a lot of things on the way. And as I tried to fix them and implement new stuff, all the time I came to new things that I wanted to fix. And having a quick look at the source code now, at the repository, at the changes compared to upstream, it kind of looks like this. So this is only the firmware, and you can see in the firmware we have around over 11,000 new lines, and a few of them are actually from UAVCAN that I didn't write, like the files here that were auto-generated, but and also this one that is the C implementation of UAVCAN, and so you can subtract probably like 3,000 lines from that, but the other ones are really new features and changes, including the UAVCAN support that, for example, works with the PixHawk flight controllers. And I will show a demo of VESC tool now, and I will point out some of the new features that require the firmware changes. And then we can also have a look at the repository for VESC tool and do the same thing. And here you can see that we have a similar amount of changes, over 10,000 new lines. And most of the stuff here is actually the QML stuff for the mobile application. And the mobile application that you see to the left now is the result of the current status, and it will look exactly the same on the phone. In fact, I also have tried it on my phone, and I will not show all the new features now, but I will show a few video demonstrations of some configurations. So here I have a setup with two VESC 6. This one is a newer version. In fact, this one has a built-in NRF51. I don't think it will come with that, but I'm not sure. And this is the old version. And here I have two completely different motors. So this one is a normal outrunner with Hall sensors, and this is also an outrunner in kind of aluminum tube with an AS5047 encoder. And what I tried to achieve as one of the goals was to make it possible to configure multiple motors at the same time and do it in a quite automatic way, especially if you want to have the VESC on a drone with UAVCAN and you have a whole bunch of motors, then you don't want to go around and configure all of them one at a time. So we can start by scanning, and this one is actually shown up as this VESC 6 Plus, and we'll connect to it. And this is what the motor setup wizard looks like in the app now, and it also looks similar in the desktop application. So essentially the new way to set up motors is that you kind of select a motor size, and from the motor size essentially derive the maximum power losses, which is the most important parameter. And then you also added some default parameters such as the open loop eRPM and the sensorless one. But in general, you can, if you want to override them, edit them manually. If your motor wouldn't show up here, then you can start by just setting a maximum amount of power losses. And the idea behind this is that if you have a motor of a given size, then the current it can handle depends on the kV. So if you have a higher kV value, then you need more current for the same torque, but you will not get the same heating, and essentially end up with a certain amount of heating per torque. And this is something you can take care of if you make the detection like this. So let's choose this motor and take the next step. And I also implemented some metadata in the VESC about the battery. So you can choose the battery type and the number of cells. Actually, we just have the no number of cells here, since I have it connected to my lab power supply and it will cut out otherwise. I will show this battery setup in my next demo. And then we go to the next page, and here you can set the gear ratio and the wheel diameter. And this is important so that the VESC and hence VESC tool can derive the speed that you ride at and how far you have been going. And together with the battery parameters, you can also see how far you will get on the charge. But let's go back to that later and run the detection. And now I run the detection on this VESC, and or I run the main thread of the detection of this VESC, and the first thing it will do is will scan the CAN bus and figure out all the other VESCs on it and start detection on them. and then it will finish its own detection and wait for the others to finish. And one thing you might notice already at this point is that the flux linkage measurement is completely rewritten from scratch. So instead of using BLDC, I'm actually using open loop FOC. And as it turns out, it works on the first try more or less every single time on every motor, and it starts much smoother and it gets slightly better estimation of the parameters. And the other new thing about the detection is that instead of manually setting the sensor, the VESC will try to put the sensor port in different modes and try if it can communicate with the sensor. So it will try the Hall sensor first, and if it finds one, it will configure that one. Then it will try the AS5047, and if it finds it, it will configure it. And I think at the moment now, actually this will take a bit more time, as the AS5047 takes a bit more time to configure. And regarding that, you might also see that it's also a bit smoother now, so instead of in one of the steps when it kind of moves a lot at a time, it makes much smaller movements. So we have the result here, and you can see that in the first motor, we found that we have Hall sensors connected, and it also figured out that it has a temperature sensor, and therefore it activated temperature compensation, and also set the base temperature, so that is fully automatic as well. And down here we see that we found an encoder, and we didn't find a temperature sensor. And if you wouldn't have any sensor plugged in at all, it will just go to sensorless mode. So now we have the motor detection done, and after that it will scan the CAN bus again, and then it will list all the devices that you can find. And here, for example, we find that the local VESC has ID 72, and the one in the CAN bus has ID 120. The IDs are like, instead of being like fixed at 0, they are calculated from the unique ID of the VESC now instead. So this is why I had to implement the CAN bus scan function. And the purpose of this page is to figure out the direction of the motor. So for example, if you look at this motor, you can try the forward button. That was the other one. This one. And you can see which direction it spins. And for example, if you have it on a wheel and this is the wrong direction, you can click the invert button. So you can go through all of your motors here and figure out which are inverted and configure that. And you can also open this dialog later from VESC tool. And once you're done here and click finish, actually the moment you click inverted, it will actually store the configuration. But then you can click finish, and then you're ready to go. You can, for example, bring up the control tab. And we could also go, no, actually let's stay at the control tab and see if you can run them. And this works quite well, as you can see. Next we have the input setup wizard, and what I will do in this case is I will plug in this PWM or PPM receiver into this VESC, which is actually the one that sits on the CAN bus. So I'm connected to this one, and I plugged in the receiver to this one, and it goes to this Matic remote. So then we do the input setup wizard, and similar to what we had before, it will scan the CAN bus and list all the VESCs you can find on it. And then you can choose which one the input is connected to. And in this case, it is this one. So we choose it and go to the next step. And then we choose PPM in this case. And then we come to the mapping. I will work on this a bit more later because it is just text now. But essentially, when you have your input, you move it from the minimum throttle to the maximum. I think this one is in power limit mode now, so I put it to full power. Then you can see that we are between 1 and 2 milliseconds, which is quite what we expect from this kind of receiver. Then we take next, and then you can it actually configure it already, so you can give it a try here. And if you need to change something, you can do that from the menu here. And then we are done with the input configuration, and then we should be ready to go. So that was quite simple. Next, we can show the real-time data. So this is, well, more or less the old page. What you see that you can see that I did here is that I styled the meters so that we have a numerical value in the center and a different cursor on them. And I also added support for horizontal location. So if you make it like wider than high, then everything changes the layout a bit. And I did this on the start page as well. So hopefully it will work quite well on tablets as well, or if you want to mount your phone horizontally. And those are the default meters. We can give them a try. You can see that we also have, whoa, that was a bit aggressive. But you can see that we have a kind of a shadow behind the cursor as well, which looks quite okay. And then we can also swipe down, and if we set the battery limits and the gearing and everything, then we can also get the speed meter and the power meter and some other values. And the interesting thing with this page is that if we have the CAN bus connected, which we do here, is that the current and the power and the amp hour and the watt hour counters are actually the accumulated values from all the VESCs found at CAN bus. So if I have a dual motor setup, then it takes that into account. And this way we can get an estimate of how many watt hours per kilometer we draw on the whole setup. And based on the battery parameters, we can estimate the range we have left. So that is really convenient. And I've been using it a lot, and it's actually quite accurate on my boards as well. So let's move on a bit with the demo. I have two webcams here. One is pointed at my Urban Carver, the Orson board, which is really a good long board. And the other one is pointed at my e-bike, which has a hub motor in the front and also one in the back. So both of them are a bit tricky setups due to having multiple motors. And the e-bike has also some extra trickiness, as you will see. So let's start by connecting to the e-bike. I know that this is the e-bike. And in case you would forget that, you can actually set a name on the device. So I will just call this one e-bike. And then we can also plug in this one and also give it a name after scanning it. Or after scanning, so it shows up in the menu here. Let's call it Urban Longboard. I think I called it Carver before. It's actually a longboard, so yeah, so it should still be connected to the e-bike. And let's do the same thing we did before. So in this case, we choose e-bike hub motor by default and do the next step. And on the e-bike, I actually have 12 cells in series and I have 15 amp hours. I actually did this before, so that's why I remember the amp hour value. And also I have direct drive because I don't have any gearbox on it, and you can just check this one or set the same number for both of those, but this one is easier to see why I did it. And then you also set the wheel diameter, and I have about 645 millimeters in diameter of the wheel. And I think most e-bike motors, those hub motors, are around 46 poles. So run the detection, see if it works. So the mounting of the e-bike is not very stable, so hopefully it doesn't fall down. So I think it finished, so it will just like collect all the values and set the battery settings. And then we can see that we found Hall sensors on both of them, which is actually the case, and not any temperature sensors since I didn't have any. And one thing you can notice here as well, I should have mentioned before as well, that given the maximum power loss of 75 watts, it derived that this motor can take about 27 amps at that power loss, and this one can take about 23. So they are a bit different, the hub motors, and they also have a bit different flux linkage values. So this one is actually, that's actually if you have a same size motor, so the flux linkage is roughly the inverse of the kV value. So this one essentially has lower kV, and if you have lower kV, then you tend to have higher resistance and more torque per amp, so this is why you can have less amps on this one. And the opposite is true for this motor. So let's go to the next page again and set up the direction. And if I remember correctly, then I'm quite lucky on this one that both of them are the correct direction by default. But if that wouldn't be the case, then you can just invert the wheel and see that yeah, it's no big deal if it's not the case. So that's it for the motor setup. It should be, and also the battery setup and everything, so that should be ready to run. And now we do the input. And the input is the tricky one on this one, because I have the Bluetooth module connected to one of the VESCs, and I have the input connected to the other one, so it was the same case that I showed before. And the other tricky part is that I'm using the ADC input, and I'm actually using two throttles, one for acceleration and one for braking. So let's do the mapping here. I will just go to the throttles and move them to the maximum value. And then we can apply the mapping data. Actually, it will be applied when I click next. And here we can set the control mode to, let's see, there are lots of them. Shouldn't set the wrong one by accident, because if we're unlucky, it can just start the motors then. But this one is current no reverse brake ADC2, meaning that ADC2 or the second channel is used for braking. So let's do that and click finish. And we can go to this meter, and I will show that I can use this one for acceleration now, or this one. And brake using this one. And this brings us to a new thing. So you saw that this one is actually limited to 25 kilometers an hour here. And I think I left that setting from before. And that new setting, that new feature is something called profiles. And I think I removed the one I had before. But essentially what you can do is you can store a set of profiles that are stored in VESC tool. And in this case, I will call this one slow, for example. And what it does when you add profile, I mean, you have quite a bunch of settings to change, but by default it will use the settings that were on the motor controller or that were active at the current time. So you can just like set the profile and add a new one, and the new one will be based on the old one, so to say. So we store this one as slow, and then we can add another one and say that it is unlimited. And essentially we can just set the speed limits to, say, 80. It will not go that fast, but at least it will not limit anything in that case. And we can start by using, actually we are using this one because I did this before for trying, but let's use this one now. And you can also notice that we can either use this one until reboot. So when you use this, for example, unlimited, and unplug power and plug it in again, then it will be back at the previous one that you had. Or you can apply it permanently. And with use until reboot, it will actually not write the settings, so you can do this while you're actually running the motor. I will see if I can manage to do it on the longboard later. So let's set this one, actually use it permanently. And then we should see that we can get up into a bit higher speed. And use the braking throttle. So around 48 kilometers an hour if there's no resistance. But I wouldn't go that fast. It's not so stable, this e-bike. But it is quite convenient. And as you can see now, we have the range estimate update and watt-hours per kilometer. And of course they're quite high now since we don't have any resistance. But again, when you're out and driving, this is actually quite accurate, and I find them really useful. And the battery meter is also incredibly useful. So now that we're at it, we can also look at a few... yeah, and by the way, once you set the profiles, they will be stored in this VESC. And if you have different setups, then you can use the same profiles in all of them, because the profiles are actually set in kilometers an hour. So the VESC itself will take the gearing and everything into account. So yeah, another thing that we can show quickly now that we're at it is that, for example, the motor configuration, we also have support for horizontal layout, that we kind of get 2 columns when you stretch it and back to 1. And we have the same thing for the apps. And another thing that is quite a convenient update, both on the mobile version and on the desktop version, is that the firmware upload, since the latest 3 firmwares or so, has support for this upload all feature. And what it does, it will upload the firmware to the connected VESC, and it will also broadcast it on the CAN bus. and upload it to all the VESCs connected on the CAN bus. So if you have a setup with like on a quad rotor with 4 VESCs, then you can upload the firmware to all of them simultaneously. And that's really convenient. So that's it for the e-bike. And now we can have a look at the longboard as well. So disconnect this one. And actually this one was connected, so it was not at the top of the menu. And then we connect the longboard. Another thing, by the way, is that we can also do the CAN bus scanning down here. I'm going a bit all over the place, but I didn't write any script or so I'm just mentioning things as I encounter them now. So I hope it's still okay to follow. So if you scan the canvas here, you can also see that we have an animation for scanning and remove the buttons. So we have this one, and we have another VESC that is ID 43 on the CAN bus. So let's do the same thing again. Motor setup, medium outrunner. Next, and this one also has 12 cells and 12 amp hours, which was set before because I did it before, but otherwise you just have to enter this value. Next, we don't have direct drive, but we actually have, let me see, I think I wrote the value on the motor. We have 1462 in gearing on this one. And we have the wheel diameter is actually correct, so we have 160 millimeter wheels. And same thing again, run detection. And I think I'm so lucky that this one also has the direction correct from the start. And the reason I did it on all my stuff is that I didn't want to have to deal with the inversion of the direction every time I update the firmware, because it makes it a bit more of a pain to update the firmware. And these also have a Hall sensor, so it will hopefully find them as well. I could also show a motor that is sensorless, but yeah, it will just show up as sensorless. And by the way, regarding difficult motors while it's detecting, I don't know if I've seen a motor like this before. This kind of EDF in-runner with like half a microhenry. This one also works in the first try in this detection, so that's really, really nice. So we got the result. And apparently like 43 amps is a good value for 50 watt losses in this motor, and that seems reasonable. And both motors are quite symmetric, it seems. So we are done. We could also try the direction, but again, I think both of them are correct already. So we finish. And now I actually have another kind of surprise maybe. And hopefully this one will be available soon. So this is a new remote controller. It's actually the Matic one that we just put another PCB in, and this one also has the NRF51 in it. It's essentially the same thing as the nunchucks I had before, but instead of using an STM32 and using an NRF24, this one uses the NRF51. So then we have a fewer chips, and in this one we actually don't have it on the CAN bus, so we take the local VESC and choose the NRF controller, and then we have the pairing function, and I will show the camera now. Click here and switch it on, and then you see that we have pairing, and this one also has a display in it, and the display shows, let's see if the camera can focus here. The display shows the battery level on the board, the battery level in the remote, how fast we're going, and how far we're gone so far. And you can double click this button now to change the direction. So the display is not, the interface is not great in the display yet, but it kind of does the trick. And it's really convenient to have the battery values and everything, and this is actually quite readable when you go. And you also have cruise control on this button, so if I give it some speed and hold this one, it will maintain the speed. And I really like the cruise control feature. So let's go back to the real-time data page or the profiles page, and I will use the remote in one of my hands here, and we can see that now give full throttle, use the unlimited one and the limited one. So this is actually really convenient and nice for when you go, if you want to change the profile on the way, even in real time. And also regarding remote, so it works. The nice thing with this one is that I'm bumping into the board all the time. So the nice thing with this remote is that it works with all the old VESC 6 that have an NRF24 in them, and hence the VESC 4 as well. And I also spent quite a bit of time on the NRF51 module, so the NRF51 can actually run Bluetooth with the phone and be connected to the remote at the same time. I can actually show a demo of that. Let's unplug this one, and then I can move the camera back to show the two motors on my desk. And I can switch on the power supply. So you see that when we unplug power, then we have, let's move this one out of the way, then it figures out the problem and can just reconnect once you have power again. Let's do this VESC 6 Plus and connect to it, and then we should be able to do the same sort of pairing to this one with the input. And done. And as you can see, we should be able to have the remote update and have the real-time data update at the same time and have the motor run from the very same Bluetooth module. And the way this works is by using the time slot API of the NRF51, so you can actually, when the Bluetooth stack is not doing anything, you can in the software ask it to use the radio for a certain amount of time. And in that time slot, I reconfigure the radio to use use the what is it called, the shock burst or the ESB protocol of Nordic to communicate with the remote. And once the Bluetooth wants the radio back, it will just give it back and let it communicate. So it alters between the remote and the Bluetooth. And it actually gives quite enough time to both of them to work well. So that was really a positive surprise, that it was quite easy to, it wasn't that easy, but it was quite doable to implement that. And the other thing is that I updated the protocol to the VESC, so you hopefully shouldn't have to do any configuration on the remote itself, and all the or on the NRF itself that is used for Bluetooth connection. All the configuration is stored in the VESC. So that's quite convenient. I think this will be my demo for now. It's probably already quite long and a bit unorganized, but hopefully I will release this within a week or two. I've been working on it for months now, but it looks like everything is starting to come together and working quite reliably. So yeah, thanks for listening.